Hey friends, Jordan here. I'll make a quick video to kind of give a couple of the areas of doing a path analysis. Now, a path analysis is a process, so it's not really just one thing as you found out some of these other statistical methods are. So this will be different depending on what you're looking for and what kind of model you're making. So the data I have here is to do with disease, and this is a study from the 90s. So probably a little outdated, but easy to use. So we have variables up here: disease, sector of the town they live in, sector of the city they live in, the class, the socioeconomic class, and the age of the person. Now, these are the variables that I'm going to be working with today for this video. So the first thing we want to do when we're thinking about regression and thinking about forming a model or doing a path analysis is we want to figure out what we want to know, what we want to ask. So I want to understand from this data, what are some things that affect disease in a person, and especially these people that were tested. So I think a good way to start, I like to do, is to just look at the correlation coefficients first off. And if you've taken stats before, you know that's a bivariate correlation. So that means that there's no order given to these variables when they're tested for a relationship. And that's why you see in your coefficients table, when you run linear regression, that's why you see zero order coefficient instead of the word bivariant, because it's not giving any order to these. Now you can do it with order, and that's important to do in certain cases. So let's just explore this data here, analyze. Let's go to correlate. Let's go to a bivariate correlation, which is not giving any order to these variables. You can see I already have them here, so move them over to your variables list from your data. So we're going to select disease, sector of the city they live in, class, socioeconomic class of the person, and age. And your correlation coefficients can be given to you here in three different ways. Now the Pearson's correlation coefficient is selected by default. Now you want to use Pearson if your data can be assumed to be normally distributed. If you have run normality tests and you fail to see that it is normal, or it's not significantly normal, you want to use just Spearman correlation coefficient, which is parametric. It uses different math. So we're going to use Pearson's for now because it's what most people use, regardless of if they know if their data is normal or not. But anyway, that's why you want to use these correlation coefficients. Now the tests of significance here, two-tailed or one-tailed, we don't know which way these relationships are going to go. So we're going to keep it on two-tailed. If we did know, we could pick one-tailed and it would be more specific to that type of test. Options here, you can get your means and standard deviations if you want to. We don't really need those for this kind of test. And then click OK. Now we can see our correlations have popped up here. Now again, these are in order because they're listed, but they're zero order in that they're not given preference, or none of them are controlled for, which we'll talk about in a minute. So if we look at disease, which is what we know we're interested in for this data, we can see that there's a significant correlation. You want to look along your significant two-tailed, your p-value here. So if you have a p-value of less than 0.05, that is significant. So you can see here that the sector of the city that the person lives in has a positive, although it be a small positive, correlation that is significant to disease. We can see here that the class of the person, is not significant, and if it was, it would not be very large at all. So this is not a significant correlation between class of the person and disease. If we look at age, we can see that it is significant. You have a p-value of 0.000 for a small positive correlation with disease. So that means as age goes up, so does disease. As the quality or the sector of the city that the person lives in changes, so does disease. And this is telling us that the class, in this sample, the class of the person does not have a relationship with disease. So this is a good way to explore your data from the very beginning when you're trying to figure out what questions to ask with any data, including behavior questions and surveys and things like that are less quantifiable at times, but still, this is what you want to look at. You want to look for relationships first. Now, we've run this, and now I understand a little bit better what I want to do for linear regression and for a path analysis. So I'm going to go back out here. We're going to analyze, and we're going to go ahead and do a regression. We're going to do linear. So we go to regression, linear. You can see here I already have it, so let's move them back over here. So you have your dependent variable, and this is where we're beginning to use kind of start modeling. We're using a linear model. So your dependent variable, when you're thinking about your path, is going to be the thing that most of your lines are drawn to. You want to understand the relationships, the coefficients from your independent variables on your dependent variables. So we're going to choose disease for this model because I want to understand better, what changes disease in these people, and I want to understand class, sector of the city, and their age will be my predictors on my criterion variable, which is disease. Now, I'm not going to do this in any other way than a standard method, so this is where you would pick your type of multivariate regression. Enter is standard. And then, of course, we have statistics here. I always like to have my collinearity diagnostics checked. It lets me know what my independent variables are measuring, and if they're measuring too much of the same thing. And if they are, you can't use them, or you need to understand them in a different way. Your plots will show you your scatter plot here. Your save options will save you a new variable in your list of variables in your data if you click any of these things. So if you're clicking these, you're going to notice that your data file is going to be getting bigger every time you run this test because it's saving them in your data list out here. So unless you want them, you don't have to click them here. Okay, let's go ahead and run this linear regression model. Okay, we can see here, the first thing that I would suggest looking at is your collinearity before you do anything. It's kind of a step-by-step process. So check your collinearity, and you can see that this is fine. The tolerance is okay. It's close to 1, which is good. If this is close to 0, you need to think about different independent variables, different predictors, because the ones you have are predicting the same thing. And your VIF numbers are okay here. You don't want these to be any higher than 10 for the same reason. Now let's look at our ANOVA. The ANOVA test, you need to interpret this as the combined effect of the model that you're running. We're running one model of the predictors, age, class, and the sector of the city on disease. So this is a total F score, and you can see that it is a significant F score. So this is what you want to understand next. This means that there is a excuse me, a linear relationship, a significant linear relationship is shown in this regression model. Thirsty. And this is good. So if you don't see any significance here when you're running your tests, you can't use it. You can't use anything that's not significantly linear as by your ANOVA. So once you find significance for the combined effects of predictors on the dependent variable disease, or whatever yours are, then you can move to your model summary and understand your R squared, and your adjusted R. So your R squared and your adjusted R are the amount or the proportion of shared variance on the dependent variable disease. So in this case, 11 to 12% of disease, which is, I would want to know, disease can lead to death, so that's a pretty important, almost 13%, is in this model shared by age, class, and sector. Now let's move down here and look at these coefficients, because this is what you're going to want to understand more as you're trying to find something to do for your path analysis or for your modeling. Now you want to look at your standardized coefficients here. So these are your relationships between each of these here, which you've chosen as your predictors, on your dependent variable disease. So for class, we look at our beta coefficient, which has the t-score of 0.612, which is not significant. The p-value of 541 here shows us that this is not a significant relationship. So what I mean is the path that you would draw, the line that you would draw between the relationship of class, socioeconomic class, on the person's disease, this would be the number you would use here, 0.043. It is not significant. So you need to let people know when you're modeling this what scores are significant and what scores are not, such as sector. So the area of the city that a person lives in has a positive 0.260 relationship with the dependent variable disease for a t-score of 3.743, which is significant at a p-value of 0.000. So this is good. You have found a significant relationship between what affects some things about the variance in disease for this person, and that is the area of town they live in. Age as well, you can see, has a standardized beta of 0.227, t-score of 3.345, with a significance score of p equals 0.001. So significant here too. Now these are what you want to use when you're modeling your path. So let's look at that for a second. Now I'm using LibreOffice, which is a free version of Microsoft Word, because I don't like to pay for big software. So LibreOffice is open source and you can use it. It's very similar to Word, but you can do the same thing in Word. So I've drawn up a document here and I'm going to show you how to put another independent variable here. Lines and arrows. I would like to draw an arrow to my dependent variable disease, label it with my little font box here. And this is the sector of town they live in, the relationship between that and disease. And we can look out here and we can remember that what we found for our coefficient on disease from the sector, our coefficient was 0.260, which was significant. So that's what we want to put on our path out here. 0.260. Now there's many different relationships you can have when you're drawing a path analysis, and these relationships can change depending on what you're asking and how these are affecting each other. So in reality, I'll draw it as an example, class is more than likely affected by the area of town that you live in. So you can see there would be a covariance here, or another relationship. Also, class that you're in may be affected, or vice versa, by how old you are. Whoops, that's not the right arrow. So age, they also have a relationship with class. Age also has a relationship to, although probably not very great, to the area of town that you live in. And so you can see that these relationships here will change, some of these relationships, and you can find the coefficients for these as well as you look for your strongest model to show the variance in disease. Now what you want to do is find the least amount of predictors with the greatest amount, or R squared, proportion of disease. So if I was to have 40 independent variables here on the left describing disease, of course I'm going to have a lot of shared variance on this independent variable here, this dependent variable, because I have so many predictors. Now, so you'd want to find really out of all those 40 which ones are really contributing to the changes on disease. And that's how you build a model. This doesn't just fall out of the software. You have to kind of go hunting for it. Okay, so in review, we have learned a little bit about looking at our regression, finding our coefficients, and also exploring our data through finding correlations. Let me find that really quick. Here it is, finding correlations between the independent variables or predictor variables that we are thinking about testing and building a path analysis model for. Okay, I hope this was helpful, and have a good day.